Feel the world at your fingertips. My long-term work for the blind. The development of Feelix for technology enthusiasts. The idea for Feelix arose by chance during the development of another one of my projects. What began as a byproduct quickly evolved into an independent innovation with the potential to fundamentally improve the lives of blind and visually impaired people. In this forward, I would like to explain the technological development of Feelix for technology enthusiasts. Feelix stands out from other systems by not only making objects, obstacles, and distances tangible, but also by transmitting colors, temperatures, brightness, electrical currents, and fine object details. By combining state-of-the-art sensors with innovative tactile feedback, the environment is captured in real time and transmitted directly to the fingertips. This makes it possible to see with the fingers, not just perceiving shapes and structures, but also recognizing colors. This sensory enhancement offers blind individuals a completely new way to experience their surroundings and move with greater safety and independence. Feelix opens the door to a new dimension of tangible vision, demonstrating how technology can expand human experience. Tactile feedback through a laser pointer. Initial insights. A laser pointer contains a tip with a diameter roughly the size of a pencil lead. The tip is mounted in a guide and can be mechanically extended and retracted by 3 millimeters from the housing, so that when retracted, it is flush with the surface of the housing. The front surface of the tip is designed to be convex, blunt. When the laser pointer's beam hits a distant object, the tip retracts into the housing. As the object approaches, the tip is pushed further out of the housing proportionally. When touching the tip with your fingertip during this process, you feel increasing pressure as the object gets closer. In my experiments with this setup, I found that it is not possible to perceive the environment with closed eyes using a single point of contact. The point-specific information is too numerous and undefined. The tip moves seemingly uncontrollably back and forth, making it impossible to create a clear image of the environment. Wide area obstacle detection, comparable to bad echolocation. In an experiment conducted by the University of Karlsruhe, a 2D pin matrix was developed and attached to the back of the test subjects. This matrix was connected to a 3D camera that captured distance information from the environment and transmitted it in real time to the corresponding pins of the matrix. This allowed the test subjects to detect obstacles and orient themselves more effectively. However, it became apparent that this setup did not enable precise detection of object details. The information was only sufficient to perceive rough structures and obstacles. After extensive training, participants were able to catch a ball using this system. The idea of the tangible line. The idea of making a line tangible came to me during the development of a 3D scanner. A laser beam is deflected through a cylindrical lens, creating a wide line, similar to an open hand fan. When this laser line is directed at various objects in a room and viewed from the side, it becomes apparent that the line is no longer straight on the objects. It bends or curves depending on whether the object is closer or farther away. The distance can then be precisely calculated using triangulation. This line can then be divided into small segments, with the distance information for each segment transmitted to a small pin. I arrange these pins side by side, creating a row of pins that together form a line. How a line became tangible, bringing my idea to life. At that time, I developed a handheld device in which the pins are arranged in a row, just like the laser line. A fan-shaped laser measures the distance of objects with the help of a camera and transmits this information to the pins. That was over 20 years ago, and with today's 3D sensors, the precision is many times greater. When placing my fingertips on the row of pins, I could feel the distance of the objects as pressure points. While testing the handheld device, I had the sensation that my fingers were extended, allowing me to touch the objects in front of me without actually making contact. The first tangible image. With my hand, I know the exact position and orientation in space from my own perspective. For example, a marksman knows exactly how to hold a pistol to hit the target, focusing only on the target itself. Similarly, when holding my handheld device and scanning the environment in front of you, a clear mental image of the surroundings forms based on what you've felt with the device, because you instinctively know where the laser line is pointing. Another example. While eating, if I close my eyes and someone places a full plate in front of me, I have no idea where the sausage is. I would first need to search with the utensils to find the sausage, cut a piece, and stab it with the fork. However, if I scan the plate once with a handheld device, I can feel the sausage without touching it. This way, I know exactly where it is and can precisely cut a piece with a knife. Learning spatial perception. For someone who has never seen, the environment is only as accessible as they can feel it with their fingers. It's difficult to imagine what large houses, trees, or even the ceiling of a room look like. The handheld device expands this awareness, providing a sense of the world one lives in. It's comparable to a sighted person trying to imagine what outer space and infinity truly look like. The bat. A pin matrix that represents the entire distance image through pressure points enables obstacle detection, comparable to a bat's echolocation. It captures rough outlines and positions of objects without providing fine details. In contrast, my system functions like a virtual extension of the fingers. It not only detects obstacles, but also allows for sensing the details of an object, even to the point of identifying a person. This opens up an entirely new dimension of tangible vision, seeing more than with the eye. My further tests focused on detecting colors, brightness differences, temperatures, and electrical currents. A switch allows these specific types of information to be added to the data transmitted to the row of pins. Contour detection and distance measurement remain continuously active. Colors with your fingertips. For example, when switching to color detection, colors are made perceptible through vibrations. The pins vibrate depending on the specific color. Red, which corresponds to the infrared spectrum, generates a slight vibration, while blue, associated with the ultraviolet range, produces a much stronger vibration. Brightness, the crosswalk. In brightness detection, dark areas are represented by slight vibrations, while bright areas produce stronger vibrations. This is particularly important for recognizing crosswalks or guiding lines on the road. Heat and electricity, the dangers. For temperature detection, I set the frequencies so that temperatures above 45 degrees Celsius generate vibrations that feel slightly painful. I applied the same principle for detecting electrical currents, where the vibrations also serve as a warning signal. How did I come up with the name? Since this is a device designed for feeling, I named it Feelix, derived from the English word feel. In Spanish, it would logically be called Centrix. This is still in my patent, waiting to be realized. My further developments are moving towards automatic detection and alert/warning systems. The following enhancements are planned. Emergency button. In situations of danger or distress, such as during an assault or accident, an alarm with the current location based on GPS data will be sent via a GSM network. Fall detection. Using an accelerometer, the system can detect if a person has fallen. If there is no response from the individual, an automatic alert will be triggered. Pattern recognition. People or objects will be identified and analyzed. If a known person or a sought-after object is detected, a notification will be sent. Integrated navigation system. This feature will guide a person safely through their environment. Voice-controlled AI. A conversational artificial intelligence will provide information about the surroundings when spoken to, and more ideas that I am not yet ready to disclose. Email. Press at feelix.world. Further information on our website, feelix.world.